Let us now look into some examples and further properties of integral ring extensions. So let's look at a geometric example. Consider the polynomial ring over some very nice field such as C, and consider as a ring extension the polynomial ring over that ring quotiented by this polynomial. So what do you think? Is this an integral extension or not? Pause and think. So the answer is this is indeed an integral extension. So we are always considering the extension r into r prime. And why is this integral? Well, because r prime is generated by the element s, and s satisfies s squared minus t squared equals 0. And now this is a scalar in R. R is already the polynomial ring in T. So this is a monic polynomial in S. We have 1 times s squared here. And so this is an integral extension. If we want to look at this geometrically, so R, the polynomial ring, is the coordinate ring of the affine line. I will draw the real part, which is just a line. And then R prime is the coordinate ring of X that looks like this. So it's the set of all points in affine 2 space such that x squared minus y squared equals 0. And by the rule of conjugates, this is x minus y times x plus y, so you get these 2 diagonal lines. And the point here is that above each point, so remember this inclusion corresponds to the projection here onto the first coordinate. Projection on. So the projection xy maps to x. In this case, it is an honest projection, and the pre-image or the fiber over any point is finite. And if you somehow think of this crossing as having multiplicity 2, whatever that means, you will see that it has the same number of points everywhere. Let's look at the next example. Same idea, but now quotient with the ideal generated by the polynomial st minus lambda for some complex number lambda. Pause and think whether this is integral or not. This is not integral. Why is that? Because the element s satisfies this polynomial and no other polynomial relation. So any polynomial equation that s will satisfy will be a multiple of this thing. And this is not monic, so this is t times s minus lambda equals 0 is what s satisfies. And this t, this is not a unit. So we cannot divide by it and get a monic polynomial. So what does this look like? Well, let's look for a few values of lambda. If lambda is equal to 0, this is st. That's just the coordinate cross projecting onto the affine line. So I'm considering r prime as the coordinate ring of this coordinate cross, and r as the coordinate ring still of the affine line. And now the problem is that the point 0 has an infinite pre-image, while all other elements have just one element in their pre-image. If instead we take lambda equals 1, then we have st minus 1 equals 0. So this is, if we draw the real points, the hyperbola, the familiar hyperbola. And the projection onto the x-axis, so to speak, now leaves the point 0 without pre-image. So this irregularity of pre-images is what we seem to avoid, at least these examples suggest, when doing integral extensions. Those were 2 geometric examples. Now let's go through some properties of these integral extensions. So first, a standard property that is a routine exercise for you to verify that the composite of two finite ring extensions is finite, and the composite of two integral ring extensions is integral. As when studying fields, you look at fields that are algebraically closed, and that means something. We want to study the equivalence now when we have replaced algebraicity of field extensions by integrality of ring extensions. So consider a ring extension, not necessarily integral, and consider the set of all points in the larger ring that are integral over the smaller ring. The claim is that this is a ring, and we will call this the integral closure of R in R prime. So why is it a ring? So if A and B are integral, then the ring extension is integral. This was the added strength to the proposition we proved earlier. So in particular, this means that all elements here are integral, such elements as A plus B and A times B. And so R bar will be closed under sums and products, and it's therefore a ring. And it's called the integral closure. If a ring is equal to its own integral closure, we say that it's integrally closed in R prime. And if we say that something is integrally closed without reference to a bigger ring, we can do this if the ring R is an integral domain. Then we say that R is integrally closed just like that, or more commonly normal, if it is integrally closed in its field of fractions. By the way, there is a stacking of terminology here. The word integral as in integral domain and the word integral as in integral extension or integrally closed, while they of course come from the same general idea, they have nothing to do with each other mathematically. So let's look at a few examples. The integral closure is integrally closed, so it makes sense to call it an integral closure. This is because of the property you proved on the previous slide that if an element is, so that the composite of integral extensions is integral. So if an element is integral over R bar, it's integral already over R, and so it's contained in R bar. Second, unique factorization domains are normal. The proof is exactly as when we showed that any rational number that is integral over the integers is an integer. So what we used there was just properties of unique factorization domains. And so any unique factorization domain is integrally closed in its field of fractions. Some further properties. One property that is handy, and the proof is left as an exercise to you, and it's a very good exercise, is that integrality is compatible with natural constructions on rings, like quotients, localization, and polynomial ring. What does this mean? So if you have an integral ring extension, if you take an ideal in the bigger ring, then its intersection with the smaller ring is an ideal in that smaller ring. And so R prime mod J is a ring extension of R mod R intersect J. And this ring extension is again integral. If you take a multiplicatively closed set in R, then it will be multiplicatively closed in R prime as well. And you will get an inclusion of rings S inverse R inside S inverse R prime. This ring extension is again integral if R into R prime is. And finally, you can consider polynomial rings, and if R into R prime is an integral extension, then RT into R prime T will be as well. These are useful properties. A more subtle property that will be useful later is something to do with the minimal polynomial. So suppose somebody gives you an element and asks you, sitting somewhere, and ask you, is this element integral over, so you look at a ring extension, and you take an element in that ring extension, and you're asked, is this integral over the base ring, yes or no? Then you have to find or show the non-existence of a monic polynomial, and in principle this is hard. This proposition simplifies this. It says the following: so if you have R, a ring extension into R prime, and assume that R is normal, this includes the statement that it is an integral domain that is integrally closed in its field of fractions. So you have this here. And assume you have an element A in R prime with the minimal polynomial P over K. So the minimal polynomial is a monic polynomial with coefficients in K of the smallest possible degree that A satisfies. And the claim is that this minimal polynomial has coefficients not only in K, but in fact in R. And then there is a technical strengthening, akin to the technical strengthening of the Cayley-Hamilton theorem, that if your element A wasn't just in R prime, but in PR prime for some prime ideal P in R, then all the non-leading coefficients of the minimal polynomial are in P. Forget about this technical strengthening. What does the rest of the proposition mean? It means that if you now have an arbitrary ring extension and consider an element in that ring extension. So if you have R in S and you consider an element A in S. And then you look at the field of fractions of R, call this field K. If the minimal polynomial of A has coefficients in R, then A is integral, because then you have a monic polynomial with coefficients in R that A satisfies. So P of A is equal to 0. So that part is easy. What the proposition tells you is that if the minimal polynomial does not have coefficients in R, then your element isn't integral. Because if your element were integral, then inside S you would have this ring extension that would be integral. And in that ring extension, A sits, and that if A is integral, then that ring extension would be integral, but then the minimal polynomial has to have coefficients in R, which it doesn't. So this shows that the minimal polynomial can be used to determine whether or not an element is integral, at least when the base ring is normal.